Good afternoon, everyone. Today we are going to complete Newton Raphson method of power flow solution. So far we have seen the Gauss-Seidel method and we just completed the basics of NR method as applied to various equations in the last class, and today we are going to complete this. So let's have a look at the lesson plan to see where we are. So if you see here, we have now starting from the complex power, transmission capacity. We have completed till Newton Raphson method, and we have two lessons left which will discuss Newton Raphson method and the first decoupled method. Okay, so we'll continue. Okay, power flow equations in the polar form. So we have discussed power flow equations. So we'll revise how the power flow equation appear in the polar form. The current entering any bus I is given by the voltage into the admittance or the elements of the admittance matrix. Capital Y says admittance matrix, which is given in this form, where theta, as you know, is the impedance angle and delta is the load angle. The complex power is given by VI conjugate, but if you take conjugate of both the sides, it becomes PI minus JQI, which is VI conjugate I, which becomes VI minus delta into this form. So when we separate the real and imaginary parts, we get the power flow equations to be this. Okay, VI, Vj, Yij cos theta Ij minus delta I plus delta J, and sin theta Ij minus delta I plus delta J. You know that when we neglect resistance, then theta becomes 90 degree and this equation is converted into sine form. Okay. And for small differences among angles, it simply is the function of delta I minus delta J. Okay. So as we have discussed in the last class, Newton Raphson method relies on evaluation of the Jacobian matrices, which are basically derivatives with respect to variables. So equation 3 in the previous slide are a set of non-linear, they are algebraic equations. Okay, in terms of various independent variables, voltage magnitudes and phase angle. We have two equations for each load bus and one equation for each voltage control bus. Expanding in Taylor series about the initial estimate and so on. So we get this particular Newton Raphson form. So as you see here, these are the known quantities, known. These are unknown. Okay, and this is the Jacobian. If you can see, there are four different parts of the Jacobian. You can say this is J1. Okay, so variation of P with respect to the load angle, variation of P with respect to the voltage, variation of Q with respect to the load angle, and variation of the Q with respect to the voltage. Now these are named differently, suppose J1, J2, J3, J4, H, L, M, N and so on. Okay. Okay. So now we know that these unknowns can be obtained by taking the inverse of the Jacobian and multiplying it into the scheduled powers. Okay. So more in the above equation, bus and 1 is assumed to be the slack bus. So because if you say, if you don't see any equation del P by or dou P by dou delta 1. Okay. The Jacobian matrix gives a linearized relationship between small changes in the voltage angle, small delta, and the voltage magnitude with small changes in the real and reactive power. So this is a more compact version. So J1, so what I used, I used the same. So it is J1, J2, J3 and J4 into these angles. For voltage control buses, the voltage magnitudes are known. Therefore, if M buses of the system are voltage controlled, M equations involving delta Q and delta V, the corresponding columns of the Jacobian matrix are eliminated for voltage control buses. Accordingly, there are n minus 1 real power constants and n minus 1 minus m reactive power constant. This is very important to note that the Jacobian is of the order of 2n minus 2 minus m cross 2n minus 2 minus m, and Jacobian 1 is n minus 1, and all this. You remember this because many times in the GATE exam questions are asked on the size of the Jacobian. So what are the elements of the Jacobian? The diagonal and up diagonal elements of Jacobian can be obtained using this formula. Now these formulas can be derived from the power flow and P and Q equations that we have seen in the first or second slide. So we use these equations to evaluate the Jacobians. Okay. So this is diagonal of diagonal for J1, diagonal of diagonal for J2, diagonal of diagonal elements for J3, and diagonal of diagonal elements of J4. Okay, so all these are obtained from the power flow equations. Okay, so one needs to evaluate these Jacobian elements before proceeding with the power flow. Okay, now that we know how to obtain the elements of the Jacobian, we go to the steps that are required to solve the power flow problem using the Newton Raphson method. For load buses where Pi scheduled and Qi scheduled are specified, voltage magnitude and phase angles are set equal to the slack bus values or 1 magnitude 0 angle. For PV buses where Vi and Pi scheduled are specified, phase angles are set equal to the slack bus angle or 0. For load buses, Pik, Qik are calculated from 3 given in the slide 2, here using this. Okay. Then we compute the difference in the power demand, the scheduled power and the actual power. So that is our difference in the demand, which will be used to compute the value of delta and voltage. For the voltage control buses, Pi and delta Pi are only calculated because Qi is specified there. Okay. Sorry, Qi is unspecified there because voltage magnitude is specified. The elements of the Jacobian matrix are calculated using 5 to 8. Okay. Procedure for the NR method. Continued. The linear simultaneous equation 4 are solved directly by the optimally ordered trigonal factorization Gaussian limits. All these are not required. It's just that we use the Newton Raphson method. Now, once we use this, all this point is relevant to evaluate the Jacobian in a computationally optimal way. So after we obtain the change in the load angle and the change in the voltage magnitude from the Newton Raphson power flow equation or model, then we increment the current delta and V to obtain our new delta and V. Okay. So this process is continued till the calculated real power and reactive power and the actual real and reactive power demand or the specified scheduled real and reactive power demand are very near to each other, or the difference is within a specified accuracy. So maybe 10 to the power minus 4. Okay. So this is how Newton Raphson method can be used. Now you may be required to convert this into a flow chart in your exam. Similar question is asked in the question bank. Now how to calculate the Jacobian size? So this I have taken directly from the Google AI by putting the question there. So how to calculate the Jacobian size? I have given you the formulas. First, identify the total number of buses, identify the PV buses M or generator buses, identify the slack bus, determine the unknowns. Okay. You solve for voltage angles and buses except slack, voltage magnitude at key buses. This is only for power flow solution, not for size only. See here. So we have to use this equation 2n minus m minus 2, 2n minus m minus 2, where m is number of voltage control buses. Suppose there is 100 bus system is 20 PV buses, then we got 2 into 100 minus 20 minus 2, 2 into 120 minus 2 into 2, 178 into 178. Okay. So this is the size of the Jacobian. Okay. Now the same principle can be applied to this question, which is question number 1.3.3. So we'll move to the questions. So if you see here, we are now in load flow studies, solution to the load flow problem. Okay, so now the first two were related to Gauss-Seidel method. Okay, now question number 3 related to size of the Jacobian. This is from an NPTEL course, power system analysis. Okay, the solution is given in the slide. Okay, so that we were discussing. Now question number 4 simply asks you to evaluate the various Jacobian elements. I have given the answers here, but you have to use the formula that has been given in the PowerPoint, even in the PPT presentation, so as to evaluate this. Okay. 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 I'll move to the PPT again. So this is the solution for that particular question. Go through it. 15 is the number of voltage control buses. Okay. Now for the same question, which I have given you the solution by Professor Devapriya Das of IIT Kharagpur on the course power system analysis, I asked the same question to Google AI, and this is the answer that was given. Okay. The steps, how it is computed. Total number of PV buses, you see 15 PV generators or generators, whereas there are 20 reactive power support capacitors which provide reactive power Q, and hence the total number of PV buses becomes 35. Instead of 15, it should be 35. So this is what you need to note. Okay, you need to note that the total number of PV buses are actually 35. Okay. Okay. 35, and we remove the slack bus. As always, we remove the slack bus. Okay. So the solution becomes the same, 664 cross 664 as given by Google AI. Okay. An interesting thing to note here is that the formula that is used in this particular problem is slightly different from the formula that is used here in this case. Okay. Now it is, take it as a homework to understand the relationship between this formula as it is shown here, this formula, okay, which is very useful, and compare it with how this problem has been solved, the context of this problem and the context of the formula. So it is, if you understand it, you have understood the problem of determining the size of the Newton Raphson Jacobian. Okay. Okay. So that's all about the Newton Raphson method. So as you know, we have two problems, I think, in your power system laboratory 2 under load flow experiment. Go through the code, run the code, understand how Newton Raphson method is implemented in code. Okay, how this algorithm is implemented in code. Thank you.